Mr. B. Dhanasegar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. Here we are having the subject that is theory of computation. Let me start with the recap of what we have seen in the previous episode of the same subject. We have seen the pumping lemma, that is we have the regular languages, and suppose if you want to show that some language is not coming under the regular class which is in this Chomsky hierarchy, then how do you show that? It is with the help of a tool called pumping lemma, which may be used for showing the languages non-regular language. Along with that, we have seen the closure properties of regular languages, that is the properties or the operations which could be done on one or more number of regular languages in order to produce another regular language. The reason why we are talking about the closure properties of regular languages is we want to build more complex languages from the simpler languages. So, if you want to build more languages just by the help of union or by the concatenation or even by the 0 or more number of times of some regular language, that is the closure operation, we have to find out first of all whether these kind of operations are closed under the regular languages or not. So, what are all the operations which are closed under the regular languages? So, these are all the things we have seen as far as the previous episode is concerned. So, with that we are concluding that regular languages. So, we started with regular language definition, regular expression, finite automata. It can be either the deterministic version or the non-deterministic version. Then we have seen that is how the conversions are all carried out, and finally we have seen the regular expression and finite automata to the regular expression, then showing the language that is not regular. The next class of language we are having is the context free languages. So, that is going to be the most familiar, that is part of our that is the Chomsky hierarchy. The reason why it is very important is because of this is the language which is meant for describing any high level programming language which is normally used for programming the computers. So, you may take any language like C or even Pascal or COBOL, whatever it is. If you want to describe the syntax of the language, first of all we should know some grammar for the description of the syntax of the languages. So, I mean that is the statement, how we are writing the statements. So, in order to describe the statement syntax, we want to have the context free grammar. So, with the help of the context free grammar only, we will be able to describe the syntax of every syntactic construct available in the programming languages. So, that is what these kind of languages are going to be very important. Then how we are describing this kind of languages, it is with the help of context free grammar. So, the context free grammar, which is a tool for describing the context free languages, and the next one we are having is how do you describe the language which is described by the context free grammar. That is what the language of the context free grammar, and the next one is given a grammar to find out the language of the grammar. So, how the evaluation is done or how the derivation is done. So, we start with the context free grammar, that is starting symbol of the grammar, from where we will be able to describe or derive the strings. So, how the derivations and all done. So, these are the things as far as we are having as far as this lecture is concerned. So, let me start with what a context free language first of all. So, it is generated by the context free grammars, and as far as the recognition component is concerned, in the case of regular languages, the device used for recognition of the regular language is called the finite automata. But here we are having another type of automata called push down automata. So, it is very similar to the finite automata, but only the exception is in the case of finite automata we do not have any kind of memory for storing the inputs, but whereas in the case of push down automata we have a memory and the memory is organized as a stack. It means that we have a theoretically there is an infinite amount of stack available for us. So, any amount of input or the variables or anything can be pushed onto the stack, and you can even pop out those symbols which are already pushed onto the stack. So, the memory, that is, you can remember any amount of information as far as a push down automata is concerned, but whereas it is missing in the case of finite automata. Only because of this storage we will be able to remember, or we will be able to recognize even more, there is larger class of languages than the class of language which could be recognized by a finite automata. Always we will find that the context free languages include the regular languages as a subset. It means that every regular language is going to be a context free language, but whereas the reverse not necessarily be applicable. We cannot claim that the context free languages are always going to be regular languages. So, now there is a question arising here. So, when we say that all regular languages can be recognized or a subset of the context free languages, why do we go for a different description for describing the regular languages? Actually, we are having the context free grammar for describing the context free languages. The regular languages are the subset of the context free languages. So, when we can represent or describe the regular languages using the context free grammar, why do we go for the finite automata? It is just for making the design process much easier. So, from the language perspective, if you are looking at, there are tokens available, I mean the keywords, operators, or even that is their identifiers. Then we are having the statements. The statements comprise of the various keywords or even operators or identifiers. So, if you are looking at the compiler's perspective, the first phase of the compilation is the lexical analyzer, then we are having the syntax analyzer. So, if you want to make the job in a phased manner, it is better to have different recognizers for different class of operations. That is, you have a recognizer for lexical analyzer and you have another recognizer for, that is, context free language recognition, that is for the statement syntax. So, that is the reason why we are having different, that is, devices or recognizers for both the lexical analyzer as well as for the context free analyzer or the syntax analyzer. So, that is about the description of the context free languages with the help of the push down automata. And every, that is, as far as the description of the programming languages are concerned, it is enough to have the context free grammar for us. So, you go for writing the context free grammar for describing the syntax of the programming languages, and then we will describe, or we will be able to generate any programming language, or we will be able to validate whether a programming language is going to be, or program is going to be the correct one as per the syntax of the programming language or not. Let us start with the definition for the context free grammar. So, first of all, we are having the simple definition, that is going to be a 4 tuple, that is, there are 4 number of components available in the, that is your grammar, B, T, P and S. The first one is the B, which we call it as the finite set of variables. So, the variables actually they are defining the syntactic categories. Syntactic category means every syntax, maybe the assignment statement is considered as one syntactic category, then the if statement is considered as one syntactic category, the expression may be considered as another syntactic category. So, each variable here it is actually representing a set of strings. So, we must understand what the string here is. From the regular language point of view, a string is going to be a sequence of symbols, but whereas from the context free language point of view, a string is going to be a sequence of tokens. So, what the token here is? A token is an indivisible element which is normally recognized by a finite automata. A sequence of token, now it is the description is done by the context free language. So, the string we mean by the context free language construct, or the context is exactly going to be a stream of tokens or a sequence of tokens. A sequence of tokens, whether they are available as per the description of the context free grammar is or not, is going to be by the variables which are available in the part of your context free grammar. That is the first component, and the second component is going to be the finite set of terminals. So, T is the finite set of terminals. We can even call them as lexicons. Actually, they are not equivalent to, or that is the variables, they are completely disjoint sets. So, if you are looking at any string, so what this string comprises of? Maybe if I am saying that a plus b as a string, so this string comprises of a plus and b. So, a is a lexical element, plus is another lexical element, then b is another lexical element. So, a plus b, whether it is available as per the pattern of the language or not, is now described with the help of the context free grammar. So, what this a plus b represent? It is going to be an expression. So, the variable used for describing this a plus b is going to be e, that means it is going to be an expression. The expression must relate this a plus b whether it is available as per the syntax or not. If it is going to be infix, a plus b is okay, maybe you can have a prefix expression or even a postfix expression. In that case, the rules are going to be completely different. So, here we find that the a plus b has 3 number of lexicons, a plus and b. So, all the 3 are considered as terminals, they cannot be further expanded. So, that is the meaning of the terminals. The next one is going to be a very important component of the grammar, that is going to be the set of all protections. We call it as the rules, normally which is of the form that is u derives v. So, u there will be an arrow symbol which is deriving v, that is general rule for any that is grammar, but we are talking about context free grammars. So, if it is going to be context free grammar, there are some restrictions on what should be u and what should be v. So, u is always going to be in v, that means it is going to be a variable, or otherwise we will call even it as non terminal, but how many non terminals are possible? That means u should always be a single variable or a single non terminal, whereas in the case of v it is in v union t star. So, the union is the normal operation. So, it can be either a variable or it can even be a terminal, or it can be the combination of variables and terminals any number of times including 0 times. It is because of the closure operation available for v union t. So, the left hand side it should be only one symbol, it cannot be empty. The right hand side we can have 0 or more number of symbols, possibly from the variable set or from the terminal set any number of times. So, that is the most important component of any context free grammar. And now the question is, what is going to be the language recognized by the grammar, context free grammar. So, where from we will start? That is nothing but the place where we start, that is going to be the starting symbol of the grammar. So, any string, if you want to say that that string is accepted by the context free grammar, then there should be a starting point for that, and there should be a tree or a derivation for that, and the derivation should start with the starting symbol, or the tree must have the root that is going to be starting symbol of the grammar. So, you start from only from the variable that is going to be declared as the starting symbol of the grammar. We may have more number of variables, but we cannot say that the strings which are derived from every variable will be considered as part of the language of the grammar, but only those strings which are derivable from the starting symbol of the grammar will be considered as part of the language which is recognized by the same grammar. These are the 4 components available as far as the context free grammars are concerned. So, the first one is the variables, second one is the terminals, the third one is going to be the set of all protection rules, and the last one is going to be the starting symbol of the grammar. The starting symbol always must be a variable, it should be from v, it must be unique and it must be from the variable set, it cannot be a terminal. Let us see some grammars for the context free grammars. The first one is, you have s derives 0 s 1, the pipe source it is going to be r epsilon. It means that for this s we are having 2 number protection rules. The first one with right hand side it is 0 s 1, and the second one is with right hand side epsilon. The epsilon is the one which is just a notation describing that the right hand side as empty string. So, it is capable of deriving an empty string, but whereas in the first rule we have 0 capital S 1. Actually, it is not given, that is what is going to be the variable set, what is the terminal set, and what is the starting symbol of the grammar, and what is going to be protection list. These are all not explicitly given as separate entities, but it is all implicit from this grammar. We have only one, that is rule, and that is having the left hand side it is going to be s. So, it must be the starting symbol of the grammar. because we do not have any other symbol or any other production rule. So, S is going to be the starting symbol, and we find that there is one 0 available on the right hand side and there is one 1 available on the right hand side. At any cost, we cannot redefine the meaning of 0. Similarly, we cannot redefine the meaning of 1. It means no further expansion is possible for 0 or for 1. So, it means that 0 is going to be a terminal and 1 is also going to be a terminal. So, now every time when you are expanding this S, it will be either introducing, that is, a 0 on the left hand side and a 1 on the right hand side, or that is going to be the end of the derivation. That is, if I am expanding this S by epsilon, then it is going to be the end of this expansion. So, you can keep on expanding this S by either 0 S 1 or it is simply epsilon. So, if you look at what will be the set of all strings generated by this S, it is going to be n number of zeros followed by n number of 1s, and that n could be even 0 also. But when n becomes 0, the output generated by the starting symbol of the grammar, that is the S, is going to be epsilon, that is going to be the empty string of the language. So, this language or the language of this grammar includes even empty string also. I will go for a break. After a short break, we will continue the lecture. Welcome back. Let us see, that is the next grammar we are having, that is as far as this example set are concerned. We have once again one variable that is going to be S. There are three rules available for us now. One is A capital S, B capital S, it is otherwise you start with B capital S, A capital S, or it is going to be once again epsilon. So, every time this S could be expanded by using any one of these three set of rules. So, if I am starting with the first one, there will be one A and one B will be introduced, and if it is going to be second one, one B and one A will be introduced, and every time there will be two number of S's introduced, and those S's can once again be replaced by either a derivation starting with A or with B or even with epsilon. So, whatever be the number of times we are expanding this S by the first alternate or the second one or even the third one, we will always find that the number of A's introduced will be equal to the number of B's introduced every time. So, if I straight away go for the third rule, it is going to be 0 times A and 0 times B. The first rule means 1 time A and 1 time B. The second rule once again 1 time A and 1 time B. So, every time if it is going to be the first one or second one, 1 A and 1 B will be introduced. If it is going to be third one, there will be 0 number of A's and 0 number of B's introduced. So, the language is going to be the set of all strings with the equal number of A's and B's. Here we have another example, that is S, it is deriving opening bracket S closing bracket, or S followed by S, or it is going to be epsilon. So, it is a very simple grammar that is normally used for recognizing the set of all balanced brackets. So, every time when I am introducing or expanding this S by the first rule, it is S is deriving opening bracket capital S and closing bracket, there will be one opening bracket and one closing bracket introduced. I can even go for expanding this S by the second rule, it is S and S. So, once again it must be expanded either by epsilon or by the first rule or even by the second rule. So, if I go for the first rule, definitely I will introduce one opening bracket and one closing bracket. So, always this will generate equal number of opening and closing brackets, but in the order expected by the conventional scenario. That is only a opening bracket followed by closing bracket, it is not the closing bracket followed by the opening bracket. The next grammar is the most familiar one. Normally when we are writing the expressions will be of the form an expression plus another expression or expression multiplied by another expression, but here we find that the expressions are having a prefix either plus or multiplication, or it is going to be simply x and y. So, you take the first rule, it is going to be the prefix equivalent of e plus e. The second one is the prefix equivalent of E star E, and the third one is prefix equivalent of X, and the fourth one is prefix equivalent of Y. When you are looking at the expressions with the single identifiers, definitely that identifier itself is available in both, that is your infix or in prefix or even in the postfix also. But in the case of operators, like suppose if I am having a binary operator plus, then if it is going to be prefix, you put the operator first, then you go for that is expression followed by an expression. In the case of postfix, it is going to be expression, expression, and followed by that we will be writing the operator. So this grammar will recognize any that is valid prefix expression. The same could be transformed into a postfix expression just by introducing the operators on the rightmost end of each production rule. In the case of your third and fourth rule, that is your small x and small y, they are simply identifiers. So any valid prefix expression can be recognized by this particular production rule or this grammar. Now let us see that is how we are generating the language, or it is going to be the set of all strings. In simple words, the definition for language is going to be the set of all strings, but how those set of all strings are all defined or derived. So we must have some notation for describing or deriving the set of all strings which are available in the language. We can say that a string that is x is available in the language only if we could find a derivation for that string from the starting symbol of the grammar. The starting symbol of the grammar, suppose if it is yes, then we must have a derivation which is of the form that is, start with the starting symbol of the grammar, then followed by we have the derivation, the double arrow symbol, and what it gives is w. That is, if you want to say that w is in the language set of the grammar G, there must be a derivation for w from the starting symbol of the grammar, and the derivation should use only the grammar G, and how many times we are making use of the productions in the grammar is any number of times. That is, the star denotes the closure, it can be any number of times. So yes, if it is capable of deriving w using the grammar G in any number of steps, then immediately you can claim that that string is going to be there in the language set of G. The only condition for w here is it must be from T star, that is, the w should contain only terminals but no question of having variables. So this is how we are defining the language generated by a context free grammar. So the meaning of this double arrow with that is star over the double arrow and G just below the double arrow, it means that deriving, or it is equivalent to say that we are inferring strings from the variables and w is having only terminals. Let us see that is how a string like your plus star x y x is derived from the grammar, that is E derives plus EE or star EE or x or y. So you have to start from the starting symbol of the grammar, it is going to be E, that is the only symbol variable in this grammar. So you start with E and you just look at what is the first symbol available in a string to be derived, it is going to be plus. So the only choice for the expansion is the first production for E, it is going to be plus followed by E followed by E. So E derives plus EE, and the next one is you go for expanding this E. We are having once again 4 number of choices for this E, either it can be plus EE or star EE or x or even y, but the only choice that is valid for this context is going to be star EE. So it is going to be expanded by using this E is expanded by using star EE. Already there is one E available, so totally there are 3 number of E's available. The next one is you just look at what is the string which is to be derived by this grammar. So it is starting with plus already generated and star generated, now it is going to be x. So expand this E by x, then E by y, and then E by that is x. So every time we must understand that only one grammar symbol must be expanded, and that may produce one or more number of terminals, but in this grammar we find that every time only one terminal is generated, and finally we find that is all the symbols available in the string are only terminals, plus is a terminal, star, x, y and x. The final output is called the yield, or we can call even as a string available in the language, or it is going to be the content of the language generated by this grammar. But what do we get as the output of every derivation is called the sentential form. So, the output of every step produced by the expansion of this context free grammar or the production rules is called the sentential form. So, you just start with the starting symbol of the grammar, then we can go for that is recognizing or finding what is the string to be recognized. So, from the string to be recognized, you start from the root, that is start from the starting symbol of the grammar. Every time you apply the that is the relevant production rule. So, you keep producing the expanding the symbols. But now the question is, when you are looking at the sentential form, there may be one or more number of variables available for us. It is not necessary always there should be only one variable. There may be more than one variable be available in every step of the sentential form. But what is the variable we will choose for the expansion? Whether it is going to be randomly chosen or whether there is any procedure for expansion or selecting the expansion variable. If you are always following that the leftmost variable is to be expanded, then the output derivation is called the leftmost derivation. We can do it in the other ways also. Every time we can select the derivation, that is your variable which is available in the rightmost part of your derivation. If the variable is selected from the rightmost component of your derivation or the rightmost sentential form, then we will be calling the derivation as the rightmost derivation. So, if the variable is selected from the leftmost position of the sentential form, the derivation is called leftmost derivation, and if the variable is selected from the rightmost position of the sentential form, then we will be calling it as the rightmost derivation. So, based on the derivations we are using, the sentential forms are also named. So, if the sentential form is the outcome of the leftmost derivation, we will be calling it as a left sentential form, and if the sentential form results as output of the rightmost derivation, we will call it as the rightmost sentential forms. Now, the question is, why do we have two different derivations? Where do we use that? So, the context free grammar is actually used for the construction of the parser, which is a very important component of any compiler. So, when you are looking at the parser, the output is going to be a tree, that is a parse tree, or you will be otherwise calling it as a derivation tree. So, if the derivation tree construction succeeds, then it is syntactically free, that is the program is or the input is syntactically free from errors, and if there is any failure in the construction of the derivation tree, then there is a failure in recognizing the syntax, or there may be some error available in the syntax of the programming language. So, how the parse tree is constructed? Whether the tree is constructed from the root to leaves or it is from leaves to the root. So, if the construction starts from the root and proceeds to the leaves, then it is going to be the your top to bottom construction, or you will be calling it as the top down parsers, where the leftmost derivations are all used, and if the construction proceeds from bottom or starts from top bottom and it is going up to the root, then it is called the bottom up process. So, the bottom up parsers are using the rightmost derivation. So, that is what we are having two different derivations, the leftmost derivation and then we are having the rightmost derivation. Leftmost derivations are used by the top down parsers and the rightmost derivations are used by the bottom up parsers. To summarize, we have seen that is what is a context free grammar and what are all the various components of the context free grammars, and the various components, that is your variables, terminals and the that is your production rules with the help of a starting symbol of the grammar. So, then we have seen some examples for the context free grammar. So, what is going to be the language recognized by the context free grammar? So, that is going to be the set of all strings generated from the starting symbol of the grammar. Then how we are deriving the strings from the grammar? It is nothing but deriving the strings from the starting symbol of the grammar. As far as the question components are concerned, we may have the questions like define context free languages, and or otherwise you may be asked to construct the context free grammar for some specific language. What is the difference between the regular language and the context free language? Can we have the same recognizer for the context free language along with the regular languages? What are production rules? And if you want to say a production rule is in context free, what are the norms for that, what are the conditions for that? And you may be asked to write grammars for palindromes, the set of all, there is that is statements like the if statement or even the assignment statement. So, maybe any construct, maybe a case statement or an expression. So, just to find out what is going to be the construct given for you and what is the general specification of the construct, based on that you just write what is going to be the grammar for that. These are all the possible questions as far as this context free grammar is concerned. So, with this I conclude this lecture. Thank you all.